Algae is the only viable feedstock to become a meaningful substitute for petroleum due to its high oil content and lipid growth rate. Algae produces up to 200 times more oil per acre than traditional biofuel feedstocks such as corn or soybean. Algae separates and consumes hydrogen from water and carbon from CO2 faster than any growing organism on Earth. During photosynthesis, algae converts large quantities of carbon dioxide to organic material while liberating oxygen 72% by weight of consumed carbon dioxide. Algae oil can be used to make diesel fuel, jet fuel, gasoline, plastics, and solvents without the global warming effects of petroleum. Algae cake is a very valuable high-protein byproduct used for the production of nutritional food additives, vitamin supplements, animal feed, and other valuable consumer products. Ponds, lakes, oceans, and other bodies of water are natural habitats for algae. Though algae are abundant in natural habitats, they do not grow in harvestable densities in nature. Light penetration. Algae cells near the top of the water's surface are exposed to light. However, a dark zone is developed in the deeper regions due to mutual shading of algae cells, restricting photosynthesis and growth. An algae colony can only grow actively up to a depth of 3 to 4 inches. The algae cell cycle. In natural habitats, algae cells undergo photosynthesis, grow, and mature in the presence of light during daytime hours. When night falls, algae cells undergo cell division and multiply in the absence of light to complete the cell cycle. Algae have a very short cell cycle. Maximum growth and biomass accumulation of algae cells is achieved during early light periods, while maximum cell division is observed during the early hours of dark period. Under favorable conditions, many algae species are capable to undergo multiple cell cycles within a 24-hour day if the colony of algae cells is introduced to alternate dark and light periods of appropriate duration. Along with balanced nutrient and pH contents, availability of enough dissolved carbon dioxide during the light period, and availability of enough dissolved oxygen during the dark period are critical for growth and cell division. It has been observed by many researchers that the temperature luminance condition plays a critical role in growth and biomass accumulation. Under low light, high temperature, and at low temperature, high luminance conditions, photosynthesis will be low. Maximum growth rates are achieved at low temperature, low luminance, and high temperature, high luminance conditions. Algae is cultured in photobioreactors under a controlled growth environment. Though many bioreactors perform well in laboratories, scaling up bioreactors for commercial production proposes enormous challenges for many bioreactor systems. A commercial bioreactor system should be capable of holding large volumes of media at a luminance appropriate enough for active photosynthesis. It takes approximately 30 gallons of growth media to produce 1 pound of dry algae, and approximately 500 gallons of growth media to produce a gallon of oil. Light penetration depends on the cell density of an algae colony within a photobioreactor. As cell density increases, mutual shading of cells limits proper optical density to perform active photosynthesis to a depth of 3 to 4 inches. A dense culture contained in a 12-inch diameter tube placed horizontally on the ground will form an inner dark zone due to mutual shading of algae cells, negatively affecting the volume advantage. For this reason, regardless of the actual depth of the water body, horizontal bioreactor systems do not offer any substantial volume advantage over natural habitats. To perform photosynthesis, algae cells utilize only 10% of available luminance of average daylight. By improving the surface to volume ratio of the bioreactor, incident light can be distributed to a larger surface area and improve productivity. Cell cycle management. Algae have a very short cell cycle. Maximum photosynthesis and biomass accumulation occurs during the early hours of the light period, while maximum cell division occurs during the early hours of the dark period. If a colony of algae cells is synchronized and introduced to alternate dark and light periods of appropriate duration, many algae species are capable of undergoing multiple cell cycles within a 24-hour period. Culture condition management. During the light period, photosynthesis takes place. Algae cells consume CO2 and release oxygen into the media culture. However, an excessive supply of oxygen within the culture will inhibit photosynthesis. During the dark period, metabolism and cell division takes place. An excessive supply of CO2 will inhibit respiration, thus inhibiting metabolism and reproduction. By introducing the algae cells to alternate light and dark zones of appropriate duration, pH, temperature, and nutrient balance is easily maintained throughout the cell cycle. Growth phase management. Synchronization phase. Metabolic activities of the algae colony are synchronized to the same metabolic state. This enables all cells in the light zone to complete photosynthesis and all cells in the dark zone to undergo cell division simultaneously, thereby improving biomass yield. Primary propagation phase. After algae cells reach maximum density, the crop line forms parallel branches and the algae culture is diluted with fresh temperature-controlled media. Advanced propagation phase. As cell density continues to increase, the algae culture is diluted with fresh temperature-controlled media and the volume of the equipment increases. Total division phase. After all cells reach maturity, they are introduced to an extended dark zone where all cells within the colony are allowed to divide in the absence of light. Maturity and lipid trigger phase. All daughter cells mature and convert maximum carbohydrates into lipids and controlled nutrient supply without dividing. Our patent-pending photobioreactor system is an arrangement of large-volume vertical bioreactors capable of holding up to 10,000 cubic meters of media per acre. Each bioreactor in the system has a dark zone and a light zone representing a complete cell cycle and achieving multiple cell cycles within 24 hours. ATC's bioreactors have a high surface-to-volume ratio of distributing incident light to the surface area of the horizontal plane to improve light exposure of media. All photosynthetic oxygen, respiratory CO2, and evaporative water are recovered and restored back into the system. Metabolic activities of the algae colony are synchronized to the same metabolic state. At one end, the system is charged with algae seed stock continuously, while harvest is collected continuously from the other end. ATC's bioreactor system regulates media temperature in relation to incident luminance to achieve maximum photosynthesis and growth. In addition to introduction of carbon dioxide in the light zone, ATC's bioreactors supplement oxygen in the dark zone to ensure healthy respiration and metabolism and to minimize conditions of fouling and culture collapse. The system supplements nutrients and pH components at each stage based on consumption during the previous stage. ATC's bioreactors are closed-looped equipment with limited contacts with atmospheres, thereby controlling contaminants and pathogens. ATC's bioreactors vary in detailed structure and performance to serve the needs for each growth phase. Though the system holds a large volume of media, it works on low energy input since media transfer from one bioreactor to another is based on gravitational flow. The system recycles water from harvest media and recovers evaporative water along with expelled gases. Water is separated from gases through condensation and recycled back into the system. ATC's bioreactors are capable of regulating media temperature in relation to incident light, making the system adaptable to most geoclimatic regions. The truth is, because of the design claims of our patent-pending photobioreactor and algae propagation technology, No other horizontal or vertical system will compare in projected energy efficiency and volume per acre by harvesting external light.